detects, recognizes. If N2 recognizes A2, then N recognizes A2. Okay, and we design it so that happens. Okay, so now, this bigger machine, big N, has two components, two machines N1, N2. We start big N, this big machine. We start it in its big N's start state here. Right? Here's your start arrow. Here's your start state. Okay. And then from this start state, we have two eta arrows. So now that's an important idea for the proof, right? I suppose the two main ones. One is create this machine with two components, if you like, two NFAs, N1 and N2, and then the other main idea, I guess, is debatable, is this idea, like start in the start state of N1, and then have these eta arrows going to the. Oh, by the way, these large circles like this, here, here, and here. The large circles represent starting states. Okay? So this would be the starting state of big N, and these two here, they're the starting states of N1 and N2, respectively. Okay? And the little small circles here, they just represent other states. Okay? Non-accept states, just other states in the finite automaton. Okay? And the double circle states, well, as usual, they are your accept states. So these would be the accept states of N1, this automaton here, and these accept states in automaton N2. Okay. Now, so we'll now construct. This is sort of the essential idea. So you got the picture. Okay. Once you understand the picture, then it's easier to understand the formal mathematics in the formal description of your N, the whole thing. And there are more details, of course, in that formal description. And that can cause you to think a bit, especially the use of these etas. How does that work? You know that if you're not a native English speaker, there's an expression in English, the devil, the hard, mischievous, annoying, whatever. The devil is in the details. Okay, you may get a contract, for example, and it looks fine until you get to the fine print, the details at the bottom of the contract, and then there are all the catches and difficult things and maybe not so nice elements of the contract. The devil, if you're right. So the devil is in the details. So similarly with a lot of these proofs, you really have to look carefully at the details in the formal specification, the 5-tuple of the machine that you're constructing, because there can be quite a lot of details, and you really need to study these formal definitions because they can be quite subtle. Right? Be warned. Right. Okay. So we got the main idea, especially this double. Eta arrow, one to one machine, one to the other. Okay, now why does this work? So now we sort of get to the proof, right? So we're given this component N1, it recognizes language A1, okay? And here's the formal definition, formal specification of machine N1, okay? Automaton N1. Finite automaton machine tend to, both myself and Sipser, we tend to use these two terms synonymously, meaning the same thing, right? Like finite automaton, that's 6 syllables, and if you just say machine, 2 syllables, it's sort of easier, especially in conversation, right? Okay, so and then we have another machine, another NFA. N2, and it recognizes A2. Here's the formal specification of this machine. Now everything's different between these two except the alphabet. Right? Assume we have keep things simple. I mean, you could have different alphabets, but then then you have to complexify your proof a bit. So we're not, by having different alphabets makes things a bit more tedious. It's already tedious. So in the text anyway, Sipser chooses to have the same alphabet. Okay. Now, so given these two NFAs, they recognise respectively language A1 and A2. We now need to construct, because it's a proof by construction, N. That's the the whole thing that has these two machines, NFAs, N1 and N2, as components, as parts. Right? And we have to construct this machine with this formal specification, okay? And its task is to recognize the union of these two languages, A1 and A2. Okay? And if we can do that, then this union, this bigger language, if you like, that results from the union of these two languages, just put all the strings together, put all the strings from A1 together with all the strings of A2, and label that bigger set. Call that's the language. That language is then the union of these two languages. Okay. Now, so if N recognizes this union, then and that's for any two languages in the set or a class of regular languages. Therefore, that union has a machine, a finite automaton, that recognizes it. And therefore this union is a regular language, right, by definition. And since that's true for any two languages, then the whole set of regular language is closed under the union, the operation union. Okay. Right, so let's go through, let's now actually construct these elements, this 5-tuple. So if we could, let's find the formal definition of this machine, this finite automaton N. It'll be an NFA, because we're using non-deterministic computation, right? Okay, so let's do it step by step. So 1, what's Q? Capital Q, the set of states that the automaton, the NFA, the machine, uses, right? Well, I guess, so this is the start state. This is Q0, the fourth one. So Q1 would be the start state of that. Q2 is the start state of this one. So that'll be Q2, that's Q1. Okay. So the set of states of N will be all N1 states and all N2 states, and this one. And that's Q0, that's the start state of big N, right? So you union these three sets. Well, this set here only has one element, Q0. Okay? So that's Q. So it's just the union of all N1 states with, the union all N2 states, union with Q0, right? So so Q, big N's states are the union of these three. That's sort of pretty obvious, right? It seems rather intuitive, so not too difficult there. Okay? So the states of big N are all the states of N1, N2 plus N, big N's start state, Q0 here. Okay, so all right, I'll just get straight on next session.